Hey everyone, in this video we're going to be talking about spur and helical gears and specifically looking at surface durability of gear teeth. We'll also be doing an example on this surface durability, and as always this video is part of a lecture series on mechanical design too. So let's get started with, before we even get into how we estimate surface durability and how we estimate some of the stresses associated on the gear tooth, let's figure out how do gear teeth wear and what are the main reasons why gear teeth can wear. And I want you to take this video a little bit as a pause and go. And this is kind of a rhetorical question and a question that you might want to ask yourself to say like, okay, what are the different ways in which gear teeth wear based on your knowledge of gears so far, and what are the different things that we think could cause gear teeth to wear. And the number one reason, and it's not really the number one reason, but one of the most common reasons is manufacturing error. So whenever we have manufacturing error, we usually have excessive wear on the gear teeth, and usually we can have catastrophic failure in this case. So manufacturing error is not something that we have to take completely away and say, oh, we live in this perfect world where there's going to be no manufacturing problems and everything is going to be perfect. In the real world, there's manufacturing error happening all the time, and it can really cause for a system to fail. And that's the case also when you talk about gear teeth and their wear. If there's only a slight deformation or something like that on the gear tooth, we can have catastrophic failure happening from that. Another way in which they wear is through a process called pitting. And the process of pitting is failure due to repetition of high contact stresses. So when you contact over and over and over, our gear teeth can fail from pitting essentially. Okay, so that's definitely one that can happen, and it usually happens in a more systematic way. We can kind of estimate how pitting is going to occur and over what time it's going to occur. So it's important for us to understand what are the contact stresses associated with our system, and how can we make sure that our system does not fail due to pitting, at least for a certain number of cycles. And once we get into the AGMA method, we're going to talk a lot more about how we can counter surface durability, but for now, pitting is one way of doing it. Another way is in which we have wear on gear teeth is if you have abnormal heat, or if you have some heat, what could happen is you could have some warping of your teeth. If you have warping of your teeth, it essentially becomes kind of like a manufacturing error, and you can have a lot of problems there. Another way in which we can have a problem is through lubrication failure. So lubrication failure is usually we need lubrication to keep the temperature down of the gear teeth, as well as lubricate the surfaces and make sure that we don't have any problems with that. If there is a lubrication failure in a gear system, you could have something called scoring, which is essentially when the surface either rips apart because of the friction or the temperature goes too high. And the final one is abrasion. So another way in which it fails is through abrasion, which is wear due to a foreign object or due to a foreign material. And this usually happens whenever you have a cooling system for your gearbox, or a place where you have your gears. You have a cooling system. The cooling system uses air or uses something from the outside, and you do have filters, but the filters can't filter everything out, and you could have something happening with a material reacting with your system. And usually abrasion is not a mechanical failure, it's actually a chemical failure. So it's a chemical reaction that would happen between the system and between the gear tooth and some chemical reaction that happened with something in the oil or something like that, something in the lubrication, for example. Okay, so based on all these errors, we're kind of going to focus on the ones that we can measure and the ones um, that we can control, right? So it's hard to control manufacturing error other than checking that your manufacturing is correct. It's easy to control heat. We can try to reduce the heat from our gears, especially if we know kind of the conditions that is going to happen. Lubrication failure hopefully won't happen. Abrasion also hopefully won't happen. So pitting is really the one that we're interested in, and we're interested in estimating our contact stress. So what we're interested in doing is to understand surface durability. We want to be able to estimate our contact stress. And we're going to do so with some information that you usually learn in lecture series before this, which would be on mechanical design 1, okay? And this would be called Hertzian theory. So we're going to use a variation of Hertzian theory to try and figure out how contact stresses are happening between the two surfaces. And what Hertzian theory says is it assumes that essentially two cylinders are rotating into each other and contacting through rotation. So if we draw it from the side, we have, for example, one cylinder like this, another cylinder mounted just under it, and we essentially have one rotating in and the other one rotating in, and they're rotating towards each other, and they're kind of rolling on each other. Now, if we think of the motion of our gear teeth are kind of doing this rolling motion through the whole surface. So if I highlight the surface, essentially we have a rolling motion that's happening on the surface of the tooth. So one way in which we can solve for durability is to say, well, let's figure it out from a surface durability standpoint, from a Hertzian theory standpoint, where we have two cylinders rolling on each other, which would mimic kind of how a gear tooth would work when it's in contact with each other, because they're essentially rolling on each other due to the involute shape that they have. Now, this surface durability estimate, we're going to go over it just because it is important to understand where it comes from. But the AGMA method, which we'll learn in the following video in this module, will then give us a new perspective into how we can solve for contact stress. So this is kind of a lecture just to inform ourselves as to how we can develop a set of working rules, and then based on that set of working rules, we're going to take it a lot further in the AGMA method and kind of follow a step-by-step methodology with much more empirical evidence as to how contact stress is actually happening. And empirical, we mean experimental. Okay, so what we can say is from Hertzian theory, we can recall a few equations, and this might not all be 100%. You might not remember all of this through this lecture, and it might be extra information that you might not need, and you will probably not need all of this information, but I'm still going to derive a little bit of the Hertzian theory so we know kind of where it comes from and how we can modify the cylinder length to some of the lengths associated with our gear, so at least we know how to translate two cylinders put together with a gear system put together so that we know what lengths we have. And then we're going to do an example problem at the end here so that we know kind of what we're talking about and we can at least apply it to a problem. The only thing that's required of you is really to understand how to apply this to a problem rather than know the whole derivation. So I'm going to write a few equations down. So I'm going to write the dictating equation between this is that P max, so pressure max, is going to be equal to 2F over pi BL. And I'll define all of these terms right now. So P max is going to be the largest surface pressure. So just the largest pressure that you could encounter on a system. Then F is the force pressing the cylinders together. So typically for a gear, you would think of the force that the gears are pushing against each other or reacting against each other. Then L is the cylinder length. Okay, so in this case, basically the width. And then B is called the half width, and it's not really a geometrical component. This is something that is developed more in Hertzian theory, but essentially it's a combination of Poisson's ratio and modulus of elasticity to try and get a value for a half width, which doesn't really stand for that, but gets us a value of Cp, which is the coefficient of elasticity, essentially. So a couple of things that we're going to write is we're going to write what modulus of elasticity is, because we obviously don't have that memorized. Okay, so it's 2f over pi L times 1 minus V1, which V1 is actually nu 1, which is Poisson's ratio, plus 1 minus V2 squared, all divided by E2. And again, you don't need to really remember this, so I'm just writing this down for more information. Times 1 over, divided by 1 over d1 over 1 over d2, and all to the power of 1/2. So this would be your half width. And so V1, V2, E1, and E2 are elastic constants. Okay, so they're material constants. So based on the material, we can find this V1, V2, E1, E2, and D1 and D2 are just cylinder diameters. So it's essentially a measure of how the system would work based on its diameter and based on the material properties. And now, if we were to adapt this system to gears, we essentially could adapt the whole system to gears by saying, let's convert F, D, and length as into different terms that we know for gears. So it'll make sense in a second, so bear with me. So F, which is the force, is going to be equal to WT divided by cosine of phi. Okay, and we're dividing by cosine of phi because we want the whole W. We want the whole force to be taken into account, not just the tangential force in this case, because the whole force along the line of action is going to be the force between the two rolling gears, essentially. D is going to be equal to 2r. Okay, so that's just rearranging into radiuses instead. And we'll talk a little bit about the radii themselves, because the radii are going to be instantaneous values of radii. So the diameter, since we have a gear tooth, the gear tooth does not have a diameter. Okay, so we can't really call a gear tooth a cylinder. So we need to kind of figure out what the radius, or what the instantaneous radius of curvature is of our gear tooth. So essentially what we're saying is, what would our gear tooth look like if it was a whole circle? Okay, and that's the radius we're trying to find. So we'll come up with an equation for this r, but we're just going to call diameter is equal to 2r, so we have it as a radius of curvature rather than diameter of curvature. The last term is L, which is the length or the width of our gears. So the depth of our gears essentially is going to be equal to F. And obviously this is confusing because F is used for force in this case, but we're getting rid of the term for F for force. And so now we're going to translate that to the F for face width. Okay, so not to be confused, but hopefully it'll make sense once we have a final equation. Okay, all these equations here are derivation equations to figure out a final equation that we're going to be using. So sigma C is sigma for contact. Okay, so it's a contact stress. We're going to write an equation for contact stress in terms of contact stress squared. And we're going to say that contact stress squared is equal to Wt divided by pi f cosine phi. And there's a little bit more information in the book, in the book associated with this course if you want to, which is mechanical design by mechanical design by Budnas, and it's Shigley's mechanical design. Okay, so if you want to look that one up, you can. There's a little bit more information in chapter 3 as well as in chapter 14 as well. And we have that this is multiplied by, we're going to convert our 1 over d1 to 1 over r1 instead, and we're going to flip them. So we're going to have 1 over r1 plus 1 over r2 for the two different cylinders in contact with each other, or the two different gears in contact with each other. And then we have these terms 1 over v1 squared, 1 or minus v1 squared over e1 plus 1 minus v2 squared over e2. Okay, and clearly we also can say that this whole term here, so if I highlight in green, I can highlight and turn the pi, and all of this term here at the bottom is going to be a constant. Okay, so we can take this constant out and call it something new. And what we're going to do is we're actually going to call this constant, and we're going to put it to the power of 1/2, and we're going to say CP is equal, and I'll write it in black just to make sense, but CP is going to be a constant, and this constant is going to be given in your formula sheet as well. So we'll look at the formula sheet really quick from module 2. So on the first page of module 2 formula sheet, we have a bunch of different values for elastic coefficient, which is CP, and you can see we have a bunch of different values for CP in English units or US units in PSI to the 1/2, and then in megapascals to the 1/2. So we have those values available there. Okay, so going back to our information here. So going back to our information, we can now say that CP is going to be equal to all of this term with pi included within the term, and we're going to put all of this term to the power of 1/2. Okay, and we're going to call that CP, and then CP can be found for every material because it's a constant. Okay, so I can rewrite really quick what is inside the brackets, but we have 1 minus V of pinion squared over E of pinion plus 1 minus V of gear squared over E of gear. So we have one pinion, one gear, and then based on the pinion and gear, we can solve for CP. Okay, and we have that to the 1/2. Then we can write that sigma C, so we're going to take out the square root, is going to be equal to minus CP times WT times, we're going to add a term, but I'm not going to add it immediately, F cosine of phi, okay, times 1 over R1 plus 1 over R2. Okay, and this is all going to be to the power of 1/2. So this would be our equation for contact stress that we could use to solve some contact stress problem if we're given a contact stress problem. Now, we're only going to do one contact stress example, and then we're not really going to use contact stress again in this manner because we're going to learn a new method called the ACMA method, which is going to be much more inclusive of everything that we have to find in a much more in-depth manner. So one thing we're going to have to add to this equation, which we've talked about before, are the dynamic effects. And the dynamic effects that are added are the same as the Lewis bending effect. Okay, so we're going to have a kV added here so that we can take into account the velocity of the gears rotating with each other. Okay, and then based on this, we can start solving some problems. Now, for these types of problems, for surface durability problems, we're going to need to know R1 and R2, which means that we're going to need to know some information about the gear and some information about the pinion as well. Okay, so not just our gear by itself, or not just our pinion by itself. So I'm going to copy over. I'm going to copy over the question that we have for this, which is in your handout as well. So let me copy it over, and then we'll get started with that question. Okay, so we have a question here that tells us that a gear drive consists of a 16-tooth, 20-degree steel spur pinion and a 48-tooth cast iron gear. Okay, so we have cast iron mixed with steel, which is going to be an interesting combination. And we have a pitch of 12 teeth per inch. And for a power input of 1.5 horsepower at a pinion speed of 700 RPM, we're told that we have to select a face width based on an allowable contact stress of 100,000 psi, or 100k psi, which is 100,000 psi. So what we can do is we can draw a quick diagram of what it would look like, but essentially we would have a first diagram that looks like this. So we would have a gear and a pinion in contact together. Okay, the gear has 48 teeth, the pinion has 16 teeth, and then we have steel for the pinion, cast iron for the gear, and our sigma C we know is going to be equal to 100,000 psi, and that is going to be our allowable contact stress. So in the same way as before, we're trying to figure out a face width that would be appropriate for contact stress. So remember, do not rearrange the equation when you're trying to verify this. You want to keep the equation in the same order, with sigma C is equal to something as a function of F if you're going to verify this. But you can rearrange the equation in order to find F if you want to. Okay, so some of the information that we're given that the diametral pitch is 12 teeth per inch. We're given that H is equal to 1.5 horsepower, I believe, in the question. Then N is equal to 700 RPM. And finally, we're given that the pressure angle is 20 degrees, which is going to be interesting and important for us to solve for. So one of the things that we need to add to our analysis that we haven't done yet is we need to write a few things that we haven't added yet to our system. And that is, what are the values of R1 and R2? So R1, and this is more theory than the example, but we want to write them down now, is we said that R1 and R2 are instantaneous. Sorry about that. Values of radii of curvature. So essentially, they're the radius that would actually be happening if we had these two systems rolling on each other. And R1, which is usually for the pinion, would be d pinion, or diameter of pinion, divided by 2, multiplied by sine of phi. And R2 would be the exact same thing, but with a gear. So d sub g for gear, divided by 2 times sine of phi. Okay, so that gives us a little bit more information that we need to know to solve the problem. Okay, so then what we can say is we can write our governing equation for surface durability. We know that we're talking about contact stress, so we're going to use our surface durability equation, which is minus Cp times Kv times Wt over F cosine phi, okay, multiplied by 1 over R1 plus 1 over R2, and that's all going to be to the power of 1/2. Okay, And then what we're going to do is we're going to rearrange that equation to solve for F, because that's what we're asked to find in the question, based on an allowable contact stress of 100, which we're just going to write that as our contact stress. So we're going to have that F is equal to minus Cp over sigma C, and I'm going to square both because we have to take the square of everything. We need to square everything first. And then we're going to multiply that by another term, which is going to be kVWT over cosine phi, okay, just to separate them a little bit. And then we have our last term, which is going to be 1 over R1 plus 1 over R2. And now we can basically solve the problem as we go. Now, one thing that we need to find, the first thing that we need to find according to the order of this is Cp, okay? And we haven't learned how to find Cp yet. So for Cp, what we can do is we can go to our Module 2 formula sheet and we can go find Cp, and we're given elastic coefficients for steel, malleable iron, nodular iron, cast iron, aluminum, bronze, tin, bronze. The problem in our problem is that we're given two different materials that are meshing together. Now, typically when gears are designed, you usually want to use the same material for both gears meshing together. In this case, they're using different materials together. So in this table, in this formula sheet, I only give you values that are associated where you would have a steel pinion and a steel gear. So we need to go a step further and we need to try and analyze what we would get. So in addition to the formula sheet, if you go to your handout for this module, if you go to the bottom of your handout for this module, I've included table 14.8 from the mechanical design book that is based on this course. And you can find here whenever you have two systems together. So you can see that this matrix would have steel, okay? And then you would have malleable iron, malleable iron together with malleable iron, and then nodular iron with nodular iron. So as you go down, you can start making mixes of materials. So we know in our case, we have a pinion material of steel. So we're going to use steel, okay? And let me use another color just so that we can see it. Okay, so we have steel, and we know that our gear material is cast iron. So we know that our gear material is cast iron. So we're going to go to steel and cast iron. And we can see that steel and cast iron would give us 2,100 square root of PSI, or 174 square root of megapascal. So we're going to use that value as Cp. Now we're going to use US units because our problem is in US units, so we're going to use square root of PSI. Okay, so we're going to go back to our problem and write that Cp is going to be equal to 2,100 square root of PSI. Okay, and then we're going to find Kv. So Kv is going to be our velocity term for our equation. So we already have sigma c. So let's change this Cp to, we have sigma c. We have the angle as well. So I'll just check it now. And then now we have to find Kv. So Kv, we have two choices. We have only one equation for the contact stress between the pinion and the gear. Now, Kv could be found for our gear and for our pinion. Now, which one should we use? So let's say we have Kv, and we know that we have steel on one side and pinion on the other side. Sorry, we have steel on one side and cast iron on the other side. So if we go to our Kv equation, if we go to our Kv choices, we have cast iron or we have steel. So which one should we choose? Well, this is a decision that we have to make. And the decision that we're going to make is we're going to go with steel, and I'm going to explain why. Okay, so we're going to use our pinion. The reason we're going to use our pinion is because our pinion rotates 3 times more. So if you think about it, 16 over 48 means that for every one rotation of your gear, you're going to have, so one rotation of your gear with 48 teeth, one tooth is going to hit once, essentially, in one rotation. Now, for every one rotation of the gear, you have 3 rotations of your pinion. That means that the pinion is going to be a lot more in demand than the gear, and the pinion is probably going to be the one that fails first in terms of surface durability. So it has to be made a little bit stronger, maybe, but we're definitely going to use this as our most dangerous item, let's say, or most likely to fail. So we're going to use our pinion, and we're going to find KV for our pinion and not for our gear. Okay, but again, this is an arbitrary decision. You could use a gear as well. The reason why we're using the pinion is because the pinion is going to contact a lot more over time. So we're going to use KV is equal to 1200 plus V over 1200. Now, if you have similar materials, if you have the exact same material, you don't have to worry about that question. You would just use the KV for both materials. And remember that V is the pitch line velocity, and the pitch line velocity is exactly the same for pinion and gear. Okay, because they're in contact with each other, the velocity of the actual gear teeth is the same. Okay, so we have 1200 plus V over 1200. We know that V, because we're using US units, we have pi dn over 12, and we have D is equal to 16 over 12 based on our information, which is equal to 1.333 inches. We just redraw this really quickly so that it's clear, 1.333 inches, and then, 1.333 feet per minute. No, that's correct, it's inches. So for diameter, we have 1.333 inches, and so velocity is going to be equal to, if we plug in all the values, we get 244.3 feet per minute. Then once we have that, we can find KV. KV is equal to 1.204. And so we know that we can add KV to the system. Now, the next term we have to find is WT based on our equation above. WT is equal to 33,000 times H over V. And that's equal to 202.6 pound force. Okay, I'm going a little bit faster through these problems just to make sure, because we already know kind of how to solve all this. Then one thing that is new is to find R1 and R2. So R1 is diameter of pinion times sine of 20 over 2. And that's going to be equal to 0.228 inches. And then we're going to do the same thing with R2. And R2 is going to be equal to 0.684 inches. Okay. Then, obviously, we had already found the diameter of our pinion. The diameter of the gear to solve for R2 is equal to 48 over 12. Okay, just so we have it in case you need to have it. And then we can solve for F, and we can say, by plugging in all of the values that we have, we can say that F is equal to 0.669 inches. And based on that, obviously one face width that we could use is 0.669. And we know that if we were to plug in different face widths, we would get a different contact stress in the original equation. So if we wanted to test our theory, we could plug in our F into here, and we could plug in a greater F into there and hopefully get a contact stress that would be lower. Okay, so that's something that you can try. And so that means that F should be, in order for our question prompt to be correct, F should be greater than or equal to 0.0669 inches. Kind of a similar thing to the example we did last time. Now, what's important here is that we can write this, but obviously if you were given the choice to give this to a manufacturer after and you actually had to manufacture a gear, you would probably choose a F that is equal to 0.75 inches, for example, or maybe 0.7 inches, something a little bit close, a little bit easier to manufacture than 0.669, especially if you're trying to just reach a maximum of that contact stress. So you always want to be under by a little bit, and you can add a safety factor if you want to, but choosing a face width that is more of a round number or 3/4 of an inch would make a lot of sense in terms of standards and all that stuff. Okay, so one last thing I want to show you for this module part, and then in the next video, we're going to go over the AGMA method through a very long example problem. It's going to take a few videos to get through. But one thing I want to show you before we end is really quickly the module 2 formula sheet and where we can find some of the information. So all the information on surface durability is essentially within this equation right here. So we have the equation for surface durability, and then in order to find CP, what we can do is we can use this table right here, and let me take out actually. So this table right here we can use, and again, if it's not possible to use that equation, then we would have to move on to the handout equation if we have two different materials and use table 14.8 as shown below, kind of like we did in this problem. So in the next video, we're going to start the AGMA method, which is going to be a different way of finding all of our terms and finding the strengths that we need. So it's going to be a completely separate entity that's going to be learned within this chapter and within this module. And we'll see you in the next video to learn about AGMA. And really, AGMA is going to be the methodology that's going to be more useful to you as an engineer, as a modern engineer. So thank you.